Good morning everyone. Today we are going to see the Cnc technology, because Cnc is computer numerical control and it is the development of ordinary lathe. I am Dr. Y. Robinson, the Professor and Head, Department of Robotics and Automation, Erode Sengundar Engineering College. So the topic today we are going to cover is the introduction to CNC and metal cutting. To look back into the history of this CNC technology, in the US Air Force commissioned Massachusetts Institute of Technology to develop the first numerically controlled machine in 1949. It was demonstrated in 1952. At 1970 to 1972, first computer numeric control machines were developed. Today, computer numerical control machines are found almost everywhere, from small job shops in rural communities to companies in large urban areas. So the definition of CNC, it is computer numerical control. The instructions are stored as a program in a microcomputer attached to the machine. The computer will also handle much of the control logic of the machine, making it more adaptable than earlier hardware controllers. When it comes to the applications of the CNC, almost everywhere it is being used, and in machining 2.5D, 3D, turning, lathes, turning center, milling centers, and then forming again 2D, plasma and laser cutting, blanking, nibbling and punching. And 3D it is rapid prototyping. Some of the sample CNC machines we are going to see. So this particular picture shows the turning center of CNC. So the turning center resembles like an ordinary lathe. The only thing is, in lathe, humans are working, and here the same operations are performed by programming, and as per the program, the microcontroller takes the program and accordingly it machines the component as required. This particular figure shows the view of a CNC milling machine, and compared with the turning center, here the job is fixed and the tools make the movement to get the desired shape. This particular figure shows CNC laser cutting machine, where we can make the components using laser cutting technology. This particular figure shows the CNC plasma cutting, which we will be seeing it later in detail. And here you can see the CNC press. Whereas all these machines, the basic difference from ordinary machines are, all are controlled by computer programming. That's the basic where we deviate from a normal technology to CNC technology. Whatever be the machine, when computer programs are used to control the process in making the component, that is called CNC technology. And this particular figure shows the CNC rapid prototyping. Again, we will be seeing in detail in the later section. Here in this particular slide, we are viewing the industries which are most affected by the CNC technology. Like starting from aerospace, the machinery, then electrical, the fabrication, automotive, instrumentation, and mold making. So almost in all the industries, the CNC technology is being implemented, and since we can make accurate components, precise one, with more number and at cheaper cost. And in the upcoming videos, we are going to see some sample products of CNC manufacturing. Automotive industry, here you can see the engine block. So this engine block is completely produced by CNC technology. And it shows the engine block of an automobile. And again in this particular figure, you can see the various parts of an automotive industry. And as you see, all these products can be manufactured using CNC technology and for its precise manufacturing. And in this particular picture, you can see a 5-axis CNC milling machine, how it performs an operation. So the figure what you see is aircraft turbine, and that is machined by the 5-axis CNC milling machine. So these kind of complicated objects also can be manufactured very precisely using CNC technology. And in this particular picture, you can see how the CNC mold making is being done. And of course, not only in automotive or aerospace industry, in electronic industry also, the CNC technology is used for manufacturing this kind of components. And as we have seen already, the rapid prototyping machine, and using that particular machine, the figures or the components showing in the figure are being manufactured. This is an example for rapid prototyping products. Now coming to the advantages of CNC, the basic thing is we make use of computers. So utilization of computers in manufacturing applications has proved to be one of the most significant advantages, and developments over the last couple of decades in helping to improve the productivity and efficiency of manufacturing systems. And advantages of CNC. The first thing is productivity. Compare with the human beings involved in manufacturing, the production rate will be less in the case of human beings being involved. Whereas when you make use of these machines, the production rate is increased. That is, the machine utilization is increased because more time is spent cutting and less time is taken by positioning. In fact, when you make use of a labor for doing this particular said above things, it will take more time and hence there is less productivity. And second point is reduce setup time. Because for setting up, once you make the setup, then continuously the machine can be used to run the program and make the components. So reduce setup time increases utilization too. And naturally the profit increases as cost decreases and as productivity increases. So that is naturally we can understand easily. And the important point is productivity through automation. So the automation term here we make use because all the processes are automated. So productivity is obtained through automation and hence that is an advantage. Now coming to the automation. What is automation? So it is any means of helping the workers to perform their task more efficiently. So a worker is working on a particular machine, so to help him to perform their task more efficiently and with less time, we make use of the term automation. And that is again transfer of the skill of the operator to the machine. So whatever the skill level the operator is having, we have to transfer it to the machine. So that is obtained by this automation. Now let us see in detail what are the transfer skill and what is the result it produces. So the muscle power. The muscle power is a transfer skill where engine-driven machine tools. So instead of making use of the muscle power of a human being, we make use of the engine-driven machine tools. So that is the first industrial revolution what we have witnessed in the revolution of industries. Manipulating skill is the transfer skill number 2, and it is nothing but mechanization, and it is the hard automation. Vision skill. So basically the accuracy of the manufacturing work is solely depending upon the vision skill of an operator. Suppose if his vision is not sufficient, then the product will not be manufactured accurately. And for avoiding this, what we use is use of position transducers and cameras. Because of using these transducers and cameras, the vision will be enhanced so that the accuracy of the manufacturing product also will be increased. So as the result is increase of accuracy and part recognition. And the last important thing is brain power. So the brain power of human being will not be always equal, and it keeps changing. Sometimes when you continuously work on a machine, you will get tired, which we call as fatigue. So fatigue is when you do a task repeatedly, your mind is getting tired, and because of that the brain power also will be reduced. So when it comes to the CNC machines, there is no question of using or making use of brain power, because once the program is done, it keeps going. The examples of CNC machines, industrial robots, soft automation, computer control of manufacturing systems. So this is the second industrial revolution. Now the efficiency of manufacturing, the cost of manufacturing and cost of material handling. So that is the one parameter for determining the efficiency of manufacturing. Productivity. Number 2, that is the average output per man hour. So per man hour is when an operator works on a machine for an hour, how much output is coming. Or say for example, one particular product for 1 hour 10 pieces are being manufactured, and for 1 hour how much we earn. So that is when an operator works on a machine, he gives a yield of 10 components, so that is the productivity. And finally, the profit is income, whatever the income we obtained minus whatever the cost spent, like including coolant oil or the electricity bill or the wages we give to the operator and so on. To convey the advantages of CNC, the quality, because quality is very, very important in fabrication and manufacturing industries. So when you manufacture a product using CNC technology, the quality is assured. Parts are more accurate, parts are more repeatable, and less waste due to low scrap. And continuing the advantages of CNC technology, reduced inventory. Because inventory, we need not do like the ordinary operators working on a machine. Because the reduced setup time here permits smaller economic batch quantities. And lower lead time allows lower stock levels. So you need not keep more stock like conventional machines. And in turn, the lower stock levels reduce interest charges and working capital requirements. And as already you have seen, the aircraft turbine, the complex shapes can be easily manufactured. Slide movements under computer control is possible. Computer controller can also calculate the steps. And in the first NC machine built in 1951 at MIT, and that is for aircraft skin milling. There it starts the complex shapes machining. Continuing the advantage here, the management control. CNC leads to CAD. CAD is computer aided design and CAM is computer aided manufacturing and process planning and production planning. Of course, whenever we talk about the advantages, always there are some drawbacks also. Here the drawbacks are like our ordinary conventional lathe, when it costs around 1 to 2 lakhs, the CNC machine costs around 12 to 15 lakhs. And again, so it is a high capital cost we need to invest for setting up a CNC technology industry. Now let's see the fundamental of basic metal cutting. The metal cutting operations, also called machining, is one of the most important manufacturing processes in industry today, as it was yesterday. What is machining? So machining is the removal of materials in forms of chips from the workpiece by shearing with a sharp tool. The main function of a machine tool is to control the workpiece cutting tool positional relationship in such a way as to achieve a desired geometric shape of the workpiece with sufficient dimensional accuracy. The machine tool provides work holding, tool holding, relative motion between tool and workpiece, primary motion and secondary motion. The primary motion, relative motion between tool and workpiece, then it goes to cutting motion and cutting speed. In the secondary motion, feed motion and feed rate. On this particular slide, you can see the classification of the chip removing methods according to the relative motion. Hope you can see clearly the black one. So this, it shows the workpiece motion, and this one is the tool motion. And here this dot refers stationary or intermittent motion, and this arrow, where like here you can see or here you can see, this is rectilinear motion, and when it is, the arrow is curved like this, where you can see here and here, that is rotary motion. And when you combine these two, this symbol, it is a resultant of rotary and rectilinear motion, which you can observe here and here. Okay. So the classification of machine tools, those using single point tools, this is a lathe, shaper, planer, boring machines, etc. Those using multi-point tools, drilling machines, milling machines, broaching machines, hobbing machines, etc. Those using abrasive tools, grinding machines and honing machines, etc. Now coming back to this CNC systems, what are the basic components? Let's see. The top, like our human being brain, we have the machine control unit, where the position transducers act like our human eyes. So our human eyes view the things and takes information to our brain, what we are seeing. Like the position transducers inform the machine control unit where the position of the tool or job or whatever it is. And like our arm, we have tool holding device and work holding devices. ISO machine tool axis definition. So as per ISO standard, the machine tool axis, like we have this Cartesian coordinates where we have x-axis, y-axis and z-axis to divide the 360 degree. In the universe, the 360 degree can be divided into 4 quadrants like 0 to 90, first quadrant, 90 to 180, second quadrant, 180 to 270, third quadrant, and 270 to 360, fourth quadrant. So here we can see the axis definition for a tool. The top diagram shows the axis for tool. So y-axis is this, and x-axis is this, and z-axis is this. And similarly, when it comes to workpiece, there you can see the negative side of the x. You can see there, and the bottom side of y and right side of z. That's how we have defined the tool axis. So here you can see data the machine tool axis definitions. So machine tool with spindle and without spindle, you can see here. And for all the 3 axes like Z, X and Y, they are given the definitions like this, which you can just go through. Okay. Now, the right hand rule for a vertical machine and horizontal machine, you can see how you can make your thumb like this and observe. So keep all the three fingers, thumb finger, point finger and middle finger like this, perpendicular to each other, gives the definition of the axis positioning for a vertical machine as well as horizontal machine. And in this figure, you can see the standard lathe coordinate system. You can see clearly when this is a chuck, automatically x-axis is here. To the left is minus direction, minus x, and right is plus x. And z is when it goes towards tail stalk, it is plus z, and when it goes towards the chuck, it is minus z. And this is a two-axis machine. And here you can see the standard milling machine coordinate system. Here it is 3 axes. So again, in the table movement, this is x here. When it goes towards the tool, it is y, and upper side it is z. In that way, 3 axes are defined for a standard milling machine. So numerically controlled machine tools. An NC machine tool is a functionality the same as a conventional machine tool. There is no much difference between a tool used in ordinary lathe and CNC lathe. The technological capabilities NC machine tools in terms of machining are no different from those of conventional ones. So when you use a drill bit, you can use it in a conventional drilling machine, and the same drill bit can be used in CNC also. The difference is in the way in which the various machine functions and slide movements are controlled. That is most important. Even though we use the same tool, how we make use of the machine functions and slide movements are important. The functions and motions such as turning the spindle on and off, setting the cutting speeds, setting the feed rate, turning the coolant on and off, moving tool with respect to workpiece, all these things are performed by machine control unit in a NC machine tool. So that is the most important thing, because all the above said things are done by the operator in case of a conventional lathe, whereas here in CNC everything is controlled by MCU. Now we discuss about automation and machine tool automation. The CNC system elements are, a typical CNC system consists of the following 6 elements. Number 1 is part program, program input device, machine control unit, drive system, machine tool, and for all these things, feedback system. So these are the 6 important elements of a CNC system. On this figure you can see the 6 elements what I discussed in the previous slide. Just take 1 or 2 minutes to observe this diagram, where you can see that when I talk about part program, see this is a part program when a punch tape comes. And to input this program, we have this program input device. But here this is the machine control unit. Like all things are given. Here this number 4 is your drive motor. and work table is here, and Z-axis motor is here, and feedback device is also there. So these are the different elements. Now the operational features of CNC machines. A CNC control system includes a velocity loop within an axis drive system and a position loop external to the axis drive system. So within the system and out of the system, we have two things. And here you can see the flow diagram of the entire thing. Okay. Now part program. So what do you mean by part program? A part program is a series of coded instructions required to produce a part. So in case of CNC machining, our aim is to produce the components that are manufactured in a conventional way. And for this, we need to write a program. So based on the program only, the machine understands what are the operations to be performed. So again, a part program is a series of coded instructions required to produce a part. A part in the sense part of a machine or component. It controls the movement of the machine tool and the on-off control of auxiliary functions such as spindle rotation and coolant on or off. The coded instructions are composed of letters, numbers, and symbols, and are arranged in a format of functional blocks as in the following example. So here you can see this N10, G01, X 5.0, Y 2.5 and F 15.0. So all these letters, numbers are having its own explanation. So for example, when I say N10 means it is a sequence number. And when I write G01, the machine will understand that it is in linear interpolation mode. And when I say X 5.0 means in the x-axis, so the x coordinate value is 5. And sometimes you can give the numbers in the units of either inches or millimeters. Again, for defining that, we have the code. Now this Y 2.5 says like x coordinate, here it is y coordinate, and it is given in 2.5 inches. And when I say F 15.0, it is feed rate, and then again you can notice that it is 15 inches per minute. Okay, so this is how a part program will look like. Now to make the program, we have to input that. So the program input device is required. The program input device is a mechanism for part programs to be entered into the CNC controller. The most commonly used program input devices are keyboards, punch tape reader, diskette drivers, through RS-232 serial ports and networks. So many input devices are available to feed the program whatever you generate. Now the brain of any CNC system is the machine control unit, as we discussed earlier. The machine control unit is the heart of a CNC system. It is used to perform the following functions: read coded instructions, decode coded instructions, implement interpolations, that is linear, circular and helical, to generate axis motion commands. Feed axis motion commands to the amplifier circuits for driving the axis mechanisms. Receive the feedback signals of position and speed for each drive axis. Implement auxiliary control functions such as spindle on off and tool change, etc. So these are the functions of a machine control unit. Now the types of CNC control system. When you want to control, what are the types? So as we know already, there are two major types of control systems are there. One is open loop control and another one is closed loop control. Open loop control systems. In open loop control systems, step motors are used. The step motors are driven by electric pulses. Every pulse rotates the motor spindle through a certain amount. By counting the pulses, the amount of motion can be controlled. Here, no feedback signal for error correction and lower positioning accuracy. So that is a problem here. The last 2 points, no feedback signal. So if at all there is an error, if you want to correct it, you have to have the feedback system. But here, since it is open loop control system, there is no feedback. Therefore, lower positioning accuracy also there. Now coming to the closed loop control systems. In closed loop control systems, DC or AC motors are used. Position transducers are used to generate position feedback signals for error correction. So unlike the open loop control system, here we have the feedback signals. So that will be used for correcting the errors whatever happened in the previous cycle. Better accuracy can be achieved, obviously, yes, but only thing it is more expensive. And this is used for large size machines, because in smaller size machines happening error is not that much. So what we do is, for large machine components, we use this closed loop control. Now control, in the sense, what is it? So we need to have a desired path. So 3-axis position control with that is encoder feedback. Based on the encoder feedback, the 3-axis position control is happening. The next is velocity control. You need to control the speed or the velocity, which is possible by tachometer feedback, and torque control that happens based on the current feedback. Now, number 2 is path generator. The tool has to travel in a path to machine the component. Okay. So that is possible by the linear interpolation or circular interpolation or complex path interpolation. Using this, we can generate the path for the design. Now, the drive system. A drive system consists of amplifier circuit, stepping motors or servo motors, and ball lead screws. The machine control unit feeds control signals, that is position and speed, of each axis to the amplifier circuits. The control signals are augmented to actuate stepping motors, which in turn rotate the ball lead screws to position the machine table. So to position the machine table, we need something to drive, because we have the electricity. So the electricity should make the machine table move. So to move the machine table, we have ball lead screws, and to rotate the ball lead screw, we have stepper motors, and to give the feedback, we have the machine control unit. The stepping motors, or they call stepper motor also. A stepping motor provides open loop digital control of the position of a workpiece in a numerical control machine. That is the purpose of having a stepper motor. The drive unit receives a direction input, clockwise or counterclockwise, and pulse inputs. For each pulse it receives, the drive unit manipulates the motor voltage and current, causing the motor shaft to rotate by a fixed angle, one step. The lead screw converts the rotary motion of the motor shaft into linear motion of the workpiece. So here the rotary motion is converted to linear motion by the lead screw. Here you can see the outline of this Debbie motor. So motor to run, we needed the electricity. So here you can see the pulse inputs are given, direction inputs. So this drive unit, it decides what should be the rotary motion for the stepping motor, and this rotary motion using this lead screw, it is converted to linear motion. Therefore, the table can move front or back. Now recirculating ball screws, because for converting the rotary motion of the stepper motor into the linear motion, these ball screws are being used. So they transform rotational motion of the motor into translational motion of the nut attached to the machine table. Therefore, the machine table can go front and back. So here you can see the photographic view of the ball screws. Accuracy of CNC machines depends on their rigid construction, care in manufacturing, and the use of ball screws to almost eliminate soap in the screws used to move portions of the machine. So here in this figure you can see the components of the recirculating ball screws. So you can see the ball screw, ball nut, and base and linear bearings. And this slide typically explains the advantages of recirculating ball screws. See the first column, you can see the parameters like inexpensive, low power use, low maintenance, high accuracy, high repeatability, high efficiency, high load capacity, and compact size. Positioning. So the positioning resolution of a ball screw drive mechanism is directly proportional to the smallest angle that the motor can turn. The smallest angle is controlled by the motor step size. Micro steps can be used to decrease the motor step size. The CNC machines typically have resolutions of 0.0025 mm or better than that. So you can see how accuracy is. It's very high resolution because of this advantages of having computer used in the conventional machines. Machine tool. The CNC controls are used to control various types of machine tools. Regardless of which type of machine tool is controlled, it always has a slide table and a spindle to control of position and speed. The machine table is controlled in the X and Y axis, while the spindle runs along the Z axis. Feedback system. The feedback system is also referred to as a measuring system. It uses position and speed transducers to continuously monitor the position at which the cutting tool is located at any particular time. The MCU uses the difference between reference signals and feedback signals to generate the control signals for correcting position and speed errors. So position error may be there or speed error may be there. So the feedback system rectifies it. So what are the feedback devices we use in CNC machines? Encoders. See, encoder is a device used to convert linear or rotational position information into an electrical output signal. So the physical parameter like linear or rotation position that is converted by this encoder as an electrical signal, which is a output. So the encoder, we have magnetic, LVDT, or optical, contacting type, or capacitive type. So the encoders may be of these types. So industrial applications of encoders. So rotary encoders are widely used with robotics because of the need in robotics. Linear encoders are widely used with machine tools. The next one is resolvers. So resolver is a rotary transformer that produces an output signal that is a function of the rotor position. So with respect to rotor position, if an electric signal is produced, then we call that device as a resolver. So here you can see the resolver with a servo motor. The servo motor containing the resolver is shown in the figure. Now the drive motors. As we discussed already, we need to convert the electric signal into mechanical one, for which we use various motors, and those motors are DC servo motors, AC servo motors, stepper motors, and hydraulic motors. The position feedback. As we discussed already, the position should be given as a feedback, then only the error correction can be done. So it's possible by the incremental encoder, quadrature, absolute encoder, the resolver, tachometer, or no feedback. When no feedback, it comes under open loop, whereas on the above 5 are the closed loop control. For example, tachometer, it is for giving the speed. Here you can see the potentiometer. So material with constant resistance per unit length properties, and the potentiometer is basically it is a proximity level, the wiper or the position can be computed. That is the use of a potentiometer. So this is how the potentiometer looks like. You can see the various forms are there. Now coming to programming side of a CNC technology, we basically make a program to produce a component based on the drawing. So it can be done either manually or we write the code directly. The computer assisted draw the cutter path, or using CAD CAM draw the part, then based on that cutter path is generated. Then the velocity feedback. As I was telling in the previous slide, tachometers, they are used to give the speed parameter. So electrical output is proposed to the rate of angular rotation in tachometers. Encoders, resolvers, and potentiometers. So basically the number of pulses per time is proposed to the rate of change of position. So whether it is an encoder, resolver, or potentiometer, they represent a change of position. So change of position, they give it as number of pulses as the output. The cutters or cutting tools of CNC machines. So the CNC cutters basically We have turning center cutters and machining center cutters. So turning center is nothing but on a lathe, and machining center is like a milling machine. The turning center cutters. So types of cutters used on CNC turning centers: carbides and other hard materials, insert, turning and boring tools. So generally we make use of carbides for the inserts so that it can cut almost all the normal materials like MS, aluminium, brass, etc. Or we go for ceramics also, and for normal things we use HSS also, drills and tabs. And here you can see the standard insert shapes. So based on the operation, the insert shapes are used or there. For example, here you can see V. So this V, it is used for profiling, and it is one of the weakest insert. And when it comes to B, so here you can see the B1, somewhat stronger, used for profiling when the angle allows it. Similarly, you can go through this T, C, W, S. For example, S is very strong, but mostly used for chamfering because it won't cut a square shoulder. 4 edges per side is there. And of course, R is the strongest insert, but least commonly used. So these are the threading and parting tools where you can see. So this particular is the insert. So in the tool we make use of the insert. So only this insert part will be involved in cutting. The other thing is just to hold the insert. Now coming to machining center cutting tools. Most machining centers use some form of HSS or carbide insert end mill as a basic cutting tool. Insert end mills cut many times faster than high-speed steel. High-speed steel end mills leave a better finish than side cutting. So these are some comparisons. And face mills that are shown in the figure flatten large surfaces quickly and with an excellent finish. Notice the engine block being finished in one pass with a large cutter. So in the figure, you can see this is a large cutter. In a single pass from this end to that end, it finishes the large material. Ball end mills, both high-speed seal and insert, are used for a variety of profiling operations such as the mold shown in the picture here. Slitting and side cutters are used when deep narrow slots must be cut. And here you can see how the drill, tap and reamers look. So common HSS tools such as drill, tap and reamers are commonly used on CNC machining centers. And note that a spot drill is used instead of a center drill. Also, spiral point or gun tapes are used for thorough through holes and spiral flute for blind holes. Rarely are hand taps used on a machining center. Of course, when sometimes required, we use hand taps also in a machining center. Now, tool holders. All cutting tools must be held in a holder that fits in the spindle. These include end mill holder, which is shown in the figure, collet holders, face mill adapters, etc. Most machines in the USA use a cat tapper, which is a modified NS 30, 40 or 50 tapper that uses a pull stud and a groove in the flange. The machine pulls on the pull stud to hold the holder in the spindle. and the groove in the flange gives the automatic tool changer something to hold onto. HSK tool holders were designed a number of years ago as an improvement to CAD tapers, but they are getting acceptance very slowly. The CNC programming. When it comes to CNC programming, offline programming linked to CAD programs, conversational programming by the operator, or manual data input MDI, or manual control using jog buttons or electronic handwheel, word address coding using standard G codes and M codes. Now the basics of NC part programming. During secondary motion, either the tool moves relative to the workpiece or the workpiece moves relative to the tool. In NC programming, it is always assumed that the tool moves relative to the workpiece no matter what the real situation is. So here it is an important point to be noted. When it comes to programming, we make sure that the tool moves relative to the workpiece, no matter what the real situation. In a real situation, the workpiece may move relative to tool, but in programs we assume as the tool moves relative to the workpiece. Okay. The position of the tool is described by using a Cartesian coordinate system. If 0, 0, 0 position can be described by the operator, then it is called floating 0. In defining the motion of the tool from the point to another, either absolute positioning mode or incremental positioning mode can be used. What is absolute positioning? In this mode, the desired target position of the tool for a particular move is given relative to the origin point of the program. Incremental positioning. In this mode, the next target position for the tool is given relative to the current tool position. The structure of a NC part program. So commands are input into the controller in units called blocks or statements. The format of the block is fixed sequential format, a tab sequential format, word address format. Let's see with an example. Assume that a building operation is to be programmed as the tool is positioned at 25.4, 12.50. So that is X, Y, Z values by a rapid movement. The tool is then advanced 10 millimeter in the Z direction at a feed rate of 500 millimeters per minute with a flood coolant on. Then retracted back 10 millimeter at the rapid feed rate and the coolant is now turned off. Now this is a program for that fixed sequential format. We write the program in this way. When it comes to tab sequential format, the same program is written in this format. And when it comes to word address format, the same is written like this. Model commands. Commands issued in the NC program that will stay in effect until it is changed by some other command like feed rate research selection, coolant selection, etc. That is model commands. Non-model commands. Commands that are effective only when issued and whose effects are lost for subsequent commands, like a dwell command which instructs the tool to remain in a given configuration the given amount of time. Okay, gentlemen, we have listened to the Cnc technology, and of course we will continue our next lecture for this CNC programming. So we'll dedicate the entire class for discussing about this CNC programming. Okay, thank you all for listening. Thanks again.